Hey everyone, me and my group will be tackling about central dopaminic signaling agents. Now, first off, my drug, which is haloperidol. Now, haloperidol is an atypical antipsychotic. It acts as a potent D2 receptor antagonist that competes with dopamine and blocks D2 receptors, primarily in the mesolimbic pathway, reduces excessive dopamine signaling, which helps control positive symptoms of schizophrenia, such as hallucinations and delusions. Now, haloperidol's D2 blockade affects multiple brain pathways. So, in the mesolimbic pathway, dopamine goes down, which reduces psychotic symptoms. In nigrostriatal pathway, dopamine goes down and may result in extrapyramidal side effects or EPS like tremors and rigidity. For the tuberoin fundibular pathway, dopamine goes down and increases prolactin levels, possibly leading to side effects like gynecomastia. In the mesocortical pathway, dopamine goes down, which results may worsen cognitive and negative symptoms in some patients. Now, while haloperidol is effective in reducing psychosis, its dopamine blockade can lead to side effects including extrapyramidal symptoms, EPS, due to nigrostriatal dopamine blockade, or tardive dyskinesia with long-term use. Next are all about its structure. So chemical name is 4,4,4-chlorophenyl, 4-hydroxypiperidino, 4-fluoro-butyrophenone. So let's break down the structure-activity relationship, which is the SAR, of haloperidol, which is a potent typical antipsychotic which belongs to the butyrophenone class. Its structure is key to its dopamine receptor antagonism. So first off, the butyrophenone core is essential for dopamine D2 receptor binding. It provides the necessary interaction with the receptor, making it defining feature of the class of antipsychotics. Next is the fluorobenzene ring, which increases lipophilicity, enhancing blood-brain barrier penetration and boosting potency. This allows effective dopamine receptor blockade in the central nervous system. Next is the tertiary amine, which is crucial for receptor interactions. It forms key electrostatic interactions with dopamine receptors, improving binding affinity and ensuring strong antagonistic action. Next is the structural modifications and how it can influence activity. Altering the butyrophenone core can affect receptor binding, which changes the fluorobenzene ring that can modify lipophilicity and CNS penetration. Then, adjusting the amine group may alter potency and side effect profiles. Haloperidol's SAR explains its strong D2 antagonism and effectiveness in treating psychosis. Understanding these structure elements is crucial for designing safe and more effective antipsychotics. Now, in conclusion and in summary, haloperidol remains a widely used antipsychotics, and the understanding of this, the MOA and the SAR, helps in designing better drugs. Now, onto my group mates and their drugs. Thank you.
Good day everyone. For this video, we're gonna tackle about the structural activity relationship of the central dopaminergic signaling agents. So there are 5 drugs that we are gonna mention, and the drug that I'm gonna explain is the ropinirole. So ropinirole is a selective dopamine agonist that has emerged as an essential pharmacological agent in the management of Parkinson's disease and restless leg syndrome. As a dopamine receptor agonist, it works by stimulating dopamine receptors, particularly D2 and D3 receptors, to compensate for the lack of dopamine activity in the brain, which is characteristic of Parkinson's disease. The clinical application of ropeneol has greatly contributed to improving the quality of life for individuals suffering from these neurological by alleviating both motor and non-motor symptoms associated with Parkinson's disease and reducing the discomfort caused by restless legs syndrome. So, a further understanding of propinerol is a selective dopamine agonist that primarily stimulates the dopamine D2 and D3 receptors. It is used for the treatment of Parkinson's disease and restless legs syndrome. Propinerol mimics the action of dopamine, a neurotransmitter that is deficient in Parkinson's disease, by binding to dopamine receptors in the brain. It helps to alleviate motor symptoms associated with Parkinson's disease, such as tremors, rigidity, and bradykinesia. It also reduces the discomfort and urge to move associated with RLS, which typically occurs during periods of rest or inactivity. Propinerol is often administered orally and typically well absorbed in the gastrointestinal tract. Its pharmacokinetics includes a relatively long half-life, which supports once or twice daily dosing. The drug is metabolized in the liver, primarily via cytochrome P450 enzymes, and excreted primarily in the urine. So the mechanism of action of propinerol works by directly stimulating dopamine receptors, particularly the D2 and D3 receptors, which are involved in motor control behavior regulation. By activating these receptors, propinerol compensates for the lack of dopamine in the brain, particularly in the striatum and other regions involved in motor coordination, leading to improved movement and control in Parkinson's disease patients and alleviating the sensations of restlessness and discomfort in those with RLS. So here we are, the structural activity of the relationship. So as you can see in the picture, that is the chemical structure of the ropeneol. So ropeneol's core structure is based on a 2,3-dihydro, 1H pyrrolo, 3,4-B quinoline, 1 scaffold, which is similar to the structure of naturally occurring dopamine. This core is crucial for its ability to bind to dopamine receptors. So, as we all know, ropeneol is selective D2 or 3 dopamine receptor agonists. The structural modifications on the molecule allows it to specifically interact with these receptors. The binding affinity is influenced by the positioning of the functional groups, for example, the ethyl group and the nitrogen. The rigid structure of the quinolinone ring enhances the specificity of D2-like receptors. The molecule's hydrophobic regions and electron distribution allows it to selectively bind to a dopamine receptor. We also have here the chemical name of the ropeneol, which is the 4,2-dipropylaminoethyl 1,3-dihydroindole 2,1. So, at the substituents at various positions, these are the substituents that interacts with each other in order to have their therapeutic effect. So, first is we have the quinolinone ring. The quinolinone ring system is responsible for the overall rigidity and flatness of the molecule, which mimics dopamine's planar structure. The carbonyl group at position 1 enhances receptor binding through polar interactions with the receptor. Next is the ethyl group. The ethyl group enhances the compound's lipophilicity, aiding in the ability to cross the blood-brain barrier, which is important for central nervous system activity. Third is the nitrogen. The nitrogen atom in the pyrrole ring plays a role in hydrogen bonding and receptor interactions, contributing to its selectivity for dopamine receptors, particularly D2 and D3. Other substituents on the aromatic rings. The aromatic rings provides the necessary interactions with the receptor's binding site, promoting high affinity for dopamine receptors, especially D2. The size and electronic properties of the substituents can significantly impact the agonistic activity. So as for now, we are done with the structural relationship activity. I hope that you get some information about the role, and there are a lot of drugs of central dopaminergic signaling agents that will be mentioned in the next videos.
Good day everyone, and today we will be discussing one of the drugs that belong to the central dopaminergic signaling agents called levodopa. Levodopa is a prodrug that is classified as a dopaminergic medication, specifically a dopamine precursor. It belongs to a class of dopa and dopa derivative dopaminergic agents, which are used primarily in the management of Parkinson's disease. Levodopa works by being converted into dopamine in the brain, thereby supplementing low dopamine levels associated with Parkinson's disease. It is commonly administered in combination with a peripheral decarboxylase inhibitor like carbidopa to prevent peripheral conversion to dopamine and enhance its effectiveness. But first, let's talk about Parkinson's disease. Parkinson's disease is a neurological disorder that results in a progressive loss of coordination and movement. Now, the neurons responsible for coordinating movement are located in a part of the brain called the striatum, which receives information from two major sources, the neocortex and the region known as substantia nigra. The cortex relays sensory information as well as plans for future action, where the substantia nigra sends dopamine that helps coordinate all of the inputs. Now, Parkinson's disease develops when the neurons connecting to the substantia nigra to the striatum progressively degenerate. So the common adverse effects of levodopa include dizziness, loss of appetite, diarrhea, dry mouth, and throat pain. The IUPAC naming of levodopa is S2-amino-3,4-dihydroxyphenylpropanoic acid. Levodopa contains the following functional groups: amino group, carboxylic group, and phenolic hydroxyl groups. Amino group is present in structure as part of the amino acid backbone, contributing to its ability to interact with enzymes like dopa decarboxylase for dopamine synthesis. It facilitates enzymatic decarboxylation, converting levodopa into dopamine in the brain. Carboxylic acid group is essential for its solubility and transport across biological membranes, including the blood-brain barrier. They aid in solubility and transport, ensuring effective delivery to the brain. And the third one is phenolic hydroxyl groups. Two hydroxyl groups attached to the aromatic ring are crucial to its role as dopamine precursor, since they are part of the dopamine's chemical structure. The phenolic hydroxyl groups are critical for mimicking dopamine's chemical structure, enabling its conversion and activity as a neurotransmitter. So how does levodopa work? Levodopa crosses the blood-brain barrier and is converted into dopamine by striatal enzymes, thereby relieving the symptoms of Parkinson's disease. But first things first, you may wonder, well, why would you use the precursor of dopamine instead of dopamine itself? And the answer is, it's because of the blood-brain barrier. Blood-brain barrier is a tightly packed layer of endothelial cells that restricts free access of molecules between the blood and the brain. Dopamine happens to be one of those molecules that cannot freely pass through this barrier. However, levodopa can, with a little bit of help. One of the biggest problems levodopa faces on its own is peripheral metabolism. There are two major enzymes in periphery which cause breakdown of levodopa before it can reach the brain, which is DDC, or the peripheral dopa decarboxylase, which converts levodopa to dopamine, and catechol O methyltransferase, or COMT, which converts levodopa into 3-O-methyl-dopa, or 3-OMD. Because of this, levodopa must be administered with another agent called carbidopa, which inhibits dopamine decarboxylase and thus reduces metabolism of levodopa in the periphery. Another agent that is used in combination with levodopa and carbidopa is entacapone, which inhibits peripheral COMT, and thus, just like carbidopa, it prolongs the time that levodopa is available to the brain. Now, levodopa is carried across the blood-brain barrier by amino acid transporter. Once inside the brain, levodopa is efficiently converted into dopamine, thus supplementing depleted dopamine levels in the midbrain. However, let's not forget that dopamine is also susceptible to breakdown by COMT as well as MAOB, which convert dopamine into 3-methoxytyramine, or 3-MP, and 3,4-dihydroxyphenylacetic acid, or DOPAC, respectively. So again, as you can see, by decreasing the metabolism of dopamine, these drugs help to increase dopamine levels in the brain. Unfortunately, because Parkinson's is a progressive disease, with time, the number of dopamine-producing neurons decreases, and fewer cells are capable of making dopamine. Taking that into consideration, some drugs have been developed to mimic dopamine and directly stimulate dopamine receptors in the brain. Now, as I mentioned, Parkinson's disease leads to dopamine depletion that leads to increased acetylcholine release, which then activates muscarinic receptors located in the neurons responsible for smooth motor control. Now, when it comes to side effects, levodopa in combination with carbidopa may cause nausea, loss of appetite, hypotension, psychiatric disturbances, and discoloration of urine, sweat, or saliva. So all in all, levodopa is a medication used to treat Parkinson's disease and other conditions. It is effective in managing symptoms such as tremors, stiffness, and bradykinesia, or slow movement, and has been used for decades and is considered a gold standard treatment for Parkinson's disease. However, its side effects include motor fluctuations, dyskinesia, and other side effects. In conclusion, levodopa is a crucial medication for managing Parkinson's disease symptoms, but its use requires careful consideration of potential side effects and limitations. And that's all, thank you. Next drug will be discussed.
Hello and welcome. I am Kishara, and we are going to dive into the fascinating world of medicinal chemistry to explore the structure-activity relationship, or the SAR, of pramipexole. This drug is a vital treatment for Parkinson's disease and restless leg syndrome. But what makes it work? Let's break it down. Pramipexole's effectiveness is on its precise molecular architecture. At its core, we have the benzothiazole ring system. This is absolutely essential for binding to dopamine receptors. Think of it as an anchor point. So studies have shown that even minor alterations to this core drastically reduce the drug's activity. Next, we have the amino-ethyl side chain. This chain, particularly the secondary amine, is crucial for interacting with the receptor's binding site. The nitrogen atom here forms K interactions, like the lock and key. Changing the length or substitution on this chain affects both potency and receptor selectivity. Now, chirality. Pramipexole is a chiral molecule, meaning it has a left-handed and right-handed form. The S enantiomer is an active form, and this stereospecificity is vital for its interaction with the dopamine receptor binding site. This is a very important concept in pharmaceutical chemistry. And lastly, the N6-butyl group is very important for good binding affinity and efficacy. Pramipexole exhibits a strong preference for the D3 dopamine receptor subtype. This selectivity is crucial for its therapeutic effects. The benzoyl core and the specific positioning of the amino ethyl side chain contribute to this selective binding. So, what does this all mean? Pramipexole's activity depends on a very specific three-dimensional arrangement for its benzoyl core and amino ethyl side chain. The S-enantiomer spatial orientation allows for optimal interaction in dopamine receptors, particularly the D3 subtype. Even subtle changes to the structure, especially around the amino ethyl side chain or the benzoyl core, can significantly impact its potency and selectivity. This is why drug design is such a delicate and precise process. To summarize, the benzoyl core, the amino ethyl side chain, the S-enantiomer chirality, and the N6-butyl group are the key players in pramipexole's SAR. These structural elements work together to ensure effective binding and selectivity at the dopamine receptor. I hope this breakdown has helped you understand the SAR of pramipexole. If you're interested in learning more, be sure to check out the links in the description and don't forget to like, subscribe, and share this video. Thanks for watching.